Welcome to the chapter Rational Numbers.
This slide presents the overview of the chapter. Learning objectives. By the end of this chapter, you will be able to
Identify the rational numbers. List the properties of the rational numbers. Represent the rational numbers on number line. Examine the rational numbers between two rational numbers. Write the decimal representation of rational numbers. Convert the decimal form into rational form.
Introduction. Before entering into the chapter, follow the instructions shown on the screen. Click each tab to know more.
We know identifying the number of same colored tiles out of total number of tiles in the above shown image. Here, the number of red colored tiles are 3 out of 16, which is represented as 3 by 16. The number of white colored tiles are 5 out of 16, which is represented as 5 by 16. Similarly, the yellow, black, green and orange colored tiles are represented as shown on the screen. We know that all the number of colored tiles are in the form of P by Q, where P and Q are integers and Q not equal to 0 and are called rational numbers represented by Q. And these numbers are also known as quotient numbers. We also know that natural number can be represented as shown on the screen. And similarly, we can express any whole numbers and integers as shown on the screen. Thus, we conclude that all the natural numbers, whole numbers and integers are also rational numbers. Do you know how to represent all the numbered colored tiles on a number line? And can you explain all the properties of rational numbers? Let us know all the properties of rational numbers under all operations. And also learn how to represent rational numbers on a number line and conversion of decimal form into rational form. Now, let us learn about properties of rational numbers. Properties of rational numbers. The properties of rational numbers are mainly classified into closure property, commutative property, and associative property. Again, each property is further explained for whole numbers, integers, and rational numbers. Now, let us learn in detail about closure property along with the operations under whole numbers, integers, and rational numbers. A set is closed under an operation if and only if the operation of any two elements of the set produces another element of the same set. If the operation produces even one element outside the set, the operation is not closed. Click each tab to know more. Let us see the closure property of operations on whole numbers. Under addition operation, it states that if two numbers are added, their sum is a whole number. For example, 2 plus 0 is again equal to 2. It concludes that the sum is always a whole number. Under subtraction, it states that the difference of two numbers is not a whole number. For example, 3 minus 6 is equal to minus 3, which is an integer. It concludes that the difference is not a whole number. Under multiplication, it states that the product of two whole numbers is again a whole number. For example, product of 7 and 0 is again 0, which is a whole number. It concludes that the multiplication of two whole numbers is always a whole number. Under division, it states that if two whole numbers are divided, the result is not a whole number. For example, 3 by 4 is equal to 0.75, which is a rational number. It concludes that the division of two whole numbers is not a whole number. Let us see the closure property of operations on integers. Under addition operation, it states that if two numbers are added, their sum is an integer. For example, 2 plus minus 1 is again equal to 1, or minus 1 plus minus 1 equal to minus 2. It concludes that the sum is always an integer. Under subtraction, it states that the difference of two integers is again an integer. For example, 4 minus 6 is equal to minus 2, which is an integer. It concludes that the difference of any two integers is also an integer. Under multiplication, it states that the product of two integers is always an integer. For example, product of 7 and minus 1 is minus 7, or the product of minus 2 and minus 5 is 10, which is an integer. It concludes that the multiplication of two integers is always an integer. Under division, it states that if two integers are divided, the result is not an integer. For example, 7 by 5 is equal to 1.4. It concludes that the division of two integers is not an integer. Let us see the closure property of operations on rational numbers. Under addition operation, it states that if two numbers are added, their sum is a rational number. For example, 1 by 2 plus 4 by 5 is equal to 13 by 10, or 2 by 6 plus 0 is equal to 2 by 6. It concludes that the sum of two rational numbers is again a rational number. Under subtraction, it states that the difference of two rational numbers is also a rational number. For example, 1 by 2 minus 3 by 4, which is equal to minus 1 by 4, or 4 by 7 minus 0 is again equal to 4 by 7. It concludes that the difference of any two rational numbers is also a rational number. Under multiplication, it states that the product of two rational numbers is always a rational number. For example, 1 by 2 into 3 by 4, which is equal to 3 by 8, or 2 by 7 into 0 is again equal to 0. It concludes that the multiplication of two rational numbers is also a rational number. Under division, it states that if two rational numbers are divided, the result is not a rational number. For example, 1 by 3 is equal to 0.3333, which is not a rational number, irrational number. It concludes that the division of two rational numbers is not a rational number. For addition, a plus b is a rational number for any two rational numbers a and b, that is, for all ab belongs to Q. Thus, a plus b belongs to Q. For subtraction, a minus b is a rational number for any two rational numbers a and b, that is, for all ab belongs to Q. Thus, a minus b belongs to Q. For multiplication, a into b is a rational number for any two rational numbers a and b, that is, for all ab belongs to Q. Thus, a into b belongs to Q. Let us do an activity on closure property. Click on the boxes which satisfy the closure property for different types of numbers. Now, let us learn in detail about commutative property along with the operations under whole numbers, integers, and rational numbers. The name itself indicates commute, which means exchange. It states that numbers can be added or multiplied in any order without changing the sum or product. Click each tab to know more. Let us see the commutative property of operations on whole numbers. Under addition operation, it states that the change in the order of two numbers does not change the result when added. For example, 1 plus 4 is equal to 5, which is also equal to 4 plus 1. It concludes that the sum is always a whole number under commutative property. Under subtraction, it states that the change in the order of two numbers changes the result when subtracted. For example, 3 minus 6, which is not equal to 6 minus 3. It concludes that the difference is not a whole number under commutative property. Under multiplication, it states that the change in the order of two numbers does not change the result when multiplied. For example, product of 7 and 6 is equal to 42, which is also equal to product of 6 and 7. It concludes that the multiplication of whole numbers is commutative. Under division, it states that the change in the order of two whole numbers changes the result when divided. For example, 2 by 4 is not equal to 4 by 2. It concludes that the division of two whole numbers is not a whole number under commutative property. Let us see the commutative property of operations on integers. Under addition operation, it states that the change in the order of two integers does not change the result when added. For example, 5 plus minus 1 is equal to 4, which is also equal to minus 1 plus 5. It concludes that addition is commutative for integers. Under subtraction, it states that the change in the order of two integers changes the result when subtracted. For example, 8 minus of minus 2 is not equal to minus 2 minus 8. It concludes that subtraction is not commutative for integers. Under multiplication, it states that the change in the order of two integers does not change the result when multiplied. For example, product of 7 and minus 3 is minus 21, which is also equal to product of minus 3 and 7. It concludes that multiplication is commutative for integers. Under division, it states that the change in the order of two integers changes the result when divided. For example, 7 by 5 is not equal to 5 by 7. It concludes that division is not commutative for integers. Let us see the commutative property of operations on rational numbers. Under addition operation, it states that the change in the order of two numbers does not change the result when added. For example, the addition of 3 by 7 and 5 by 7 and vice versa is same for both cases. It concludes that addition is commutative for rational numbers. Under subtraction, it states that the change in the order of two rational numbers changes the result when subtracted. For example, 5 by 6 minus 2 by 3 is different from 2 by 3 minus 5 by 6. It concludes that the difference of any two rational numbers is also a rational number. Under multiplication, it states that the change in the order of two rational numbers does not change the result when multiplied. For example, product of minus 3 by 5 and minus 8 by 11 is equal to 24 by 55, which is also equal to the product of minus 8 by 11 and minus 3 by 5. It concludes that the multiplication of two rational numbers is also a rational number. Under division, it states that the change in the order of two rational numbers changes the result when divided. For example, 8 by 11 when divided with 4 by 5 is not equal to 4 by 5 when divided with 8 by 11. It concludes that the division of two rational numbers is not a rational number. For addition, a plus b is equal to b plus a for any two rational numbers a and b. That is, for all a, b belongs to Q. Thus, a plus b is equal to b plus a. For multiplication, a into b is equal to b into a for any two rational numbers a and b. That is, for all a, b belongs to Q. Thus, a into b is equal to b into a. Let us do an activity on commutative property. Click on the boxes which satisfy the commutative property for different types of numbers. Now, let us learn in detail about associative property along with the operations under whole numbers, integers, and rational numbers. The associative property states that, in addition, when we add more than two numbers, the grouping of the addends does not change the sum, and similarly for multiplication. Click each tab to know more. Let us see the associative property of operations on whole numbers. Under addition operation, it states that the sum of three whole numbers remains same if the order in which their sum is changed. For example, 1 plus 2 plus 3 is same even though if there is change in their order. It concludes that addition is associative for whole numbers. Under subtraction, it states that the difference of three whole numbers is not same if the order in which their difference is changed. For example, 4 minus of 5 minus 1 is not same as 4 minus 5 of minus 1. It concludes that subtraction is not associative for whole numbers. Under multiplication, it states that the product of three whole numbers remain the same even if the grouping of the numbers is changed. For example, product of 7, 6 and 2 is same even if there is a change in their order. It concludes that multiplication is associative for whole numbers. Under division, it states that the quotient obtained by the division of three whole numbers is not the same if the order of the numbers is changed. For example, when 3 is divided with 2 by 4, we get as 6. And when 3 by 2 is divided with 4, we get 3 by 8. So, 6 is not equal to 8. It concludes that division is not associative for whole numbers. Let us see the associative property of operations on integers. Under addition operation, it states that the sum of three integers is the same if the order in which their sum is changed. For example, 5 plus of minus 6 plus 4 is same even though if there exists change in orders. It concludes that addition is associative for integers. Under subtraction, It states that the difference of three integers is not same if the order in which their difference is changed. For example, 5 minus of 6 minus 4 is not same as 5 minus 6 of minus 4. It concludes that subtraction is not associative for integers. Under multiplication, it states that the product of three integers remain the same even if the grouping of the numbers is changed. For example, product of 4 minus 1 and minus 3 is same even if there is change in their order. It concludes that multiplication is associative for integers. Under division, it states that the quotient obtained by the division of three integers is not the same if the order of the numbers is changed. For example, when 10 is divided with 2 by minus 5, we get minus 25. And when 10 by 2 is divided with minus 5, we get as minus 1. So, minus 25 is not equal to minus 1. It concludes that division is not associative for integers. Let us see the associative property of operations on rational numbers. Under addition operation, it states that the sum of three rational numbers is the same if the order in which their addition is changed. Its example is as shown on the screen. It concludes that addition is associative for rational numbers. Under subtraction, it states that the difference of three rational numbers is not same if the order in which their difference is changed. Its example is as shown on the screen. It concludes that subtraction is not associative for rational numbers. Under multiplication, it states that the product of three rational numbers remains the same even if the grouping of the numbers is changed. Its example is as shown on the screen. It concludes that multiplication is associative for rational numbers. Under division, it states that the quotient obtained by the division of three integers is not the same if the order of the division is changed. Its example is as shown on the screen. It concludes that division is not associative for rational numbers. For addition, a plus of b plus c is equal to a plus b plus c for any three rational numbers a, b and c, that is for all a, b, c belongs to Q. A plus of b plus c is equal to a plus b plus c. For multiplication, a into b into c is equal to a into b into c for any three rational numbers a, b and c, that is for all a, b, c belongs to Q. A into b into c is equal to a into b into c. Let us do an activity on associative property. Click on the boxes which satisfy the associative property for different types of numbers. Let us do an activity on rational numbers. Drag the suitable answer from Group B for Group A and drop it in boxes provided against A. Let us do a lab activity on multiplication and division of rational numbers. Click each tab to know more. The objective of this activity is to understand how to multiply and divide the rational numbers and solve problems based on multiplication and division of rational numbers. The materials required for this activity are strips of paper, a pencil, color pens, and a chocolate bar. Let us see the procedure to find the product of 1 by 4 and 1 by 3. Take the chocolate bar and represent it as 1 unit. Divide the bar into 4 equal parts vertically. One part of it represents 1 by 4. Then divide each fourth into 3 equal parts horizontally as shown. Here one part of the horizontal division represents 1 by 3. There will be 12 equal sized pieces and one piece represents 1 by 12, that is 1 by 3 of 1 by 4. Let us see the procedure to find the division of 4 by 5 when divided with 1 by 2. Take the strip of paper and divide it into 5 equal parts and shade 4 parts. Now, divide each of 4 shaded parts into halves as shown. As there are 5 parts, each part represents 1 by 5. The 4 shaded parts represent 4 by 5. As further, the 4 shaded parts are divided into halves, which represent 8 subparts out of 5 original parts. That is 4 by 5 divided by 1 by 2, which is equal to 8 by 5. Let us answer the following questions. Shruti made 8 sandwiches for some street children. She has cut each sandwich into 4 triangular pieces. If one child can take only one piece, how many children can she feed? Procedure to answer the above question is as follows. Take 8 square-shaped sandwiches. Divide each sandwich into 4 equal parts as shown. Since there are 4 fourths in one sandwich, there will be 4 into 8 equal to 32 triangular pieces and hence 32 children will be fed. A pizza is divided into 10 equal parts. Raghu had 1 by 2 of 3 by 5 of the pizza. What whole part did Raghu have? Procedure to answer the above question is as follows. Take the pizza, divide it into 10 equal slices as shown. Then consider 5 slices of pizza from the total 10 slices. Now, out of 5 slices of pizza, consider 3 slices. So 1 by 2 into 3 by 5 is equal to 3 by 10. So, Raghu had 3 by 10 of the whole pizza. From the above activity, we observe that to multiply rational number in fraction form, simply multiply the numerators and denominators, that is a by b into c by d is equal to ac by bd, where b and d are not equal to 0. To divide rational number in fraction form, take the reciprocal of the second fraction and multiply it by the first fraction, that is a by b. When divided with c by d, we get a by b into d by c, which is equal to ad by bc, where b, c and d are not equal to 0. The above activity clearly demonstrates the procedure to multiply or divide 1 are more rational numbers. Role of 0. It states that if p is a rational number, then addition of 0 to the rational number p again results a rational number p. Statement: p plus 0 is equal to p and 0 plus p is equal to p. For example, when we add 0 and 3, we obtain 3 as result. And also when we add 2 by 5 and 0, we again get the number 2 by 5. Note: integer 0 is the identity under addition or additive identity. Role of 1. It states that if p is a rational number, then by multiplying it with 1, the result will be the same rational number as the product. Statement: p into 1 is equal to p and 1 into p is equal to p. For example, when multiply 3 with 1, we get the result as 3. And also when we multiply 1 with 17 by 7, we again get 17 by 7. Note: integer 1 is the identity under multiplication. Existence of inverse. Existence of inverse is of two types. They are additive inverse and multiplicative inverse. Click each tab to know more. Additive inverse. If a and b are the two rational numbers such that a plus b is equal to b plus a equal to 0, then b is called the additive inverse of a or negative of a. The additive inverse of the rational number p is denoted by minus p. Example: 6 by 2 plus minus 6 by 2 equal to 6 minus 6 by 2 equal to 0. Here minus 6 by 2 is the additive inverse or negative of 6 by 2 and vice versa. Therefore, minus 6 by 2 and 6 by 2 are called the additive inverse of each other. Multiplicative inverse. If the product of two numbers is 1, then we say that the two numbers are multiplicative inverses of each other. Statement: the reciprocal of a rational number p by q is q by p, whose product is always 1, and its reciprocal is represented by p by q inverse. Example: the reciprocal of 3 by 5 is 5 by 3, since 3 by 5 into 5 by 3, which is equal to 1. Distributivity of multiplication over addition. The distributive property states that multiplying a sum by a number gives the same result as multiplying each addend by the number and then adding the products together. Statement: a into b plus c equal to ab plus ac for addition. A into b minus c equal to ab minus ac for subtraction. Let us consider the three rational numbers 7 by 2, 3 by 7 and 2 by 5. By solving we get LHS equal to 29 by 10. Let us represent it as 1. RHS equal to 29 by 10. Let us represent it as 2. As both LHS and RHS are equal, we say that multiplication is distributive over addition of two rational numbers.
Knowledge check. Attempt the following questions to check your understanding.
Let us solve some example problems on properties of rational numbers. Write the additive and multiplicative inverse for the following rational numbers. A. 5 by 8. Solution. The additive inverse of 5 by 8 is minus 5 by 8. Because 5 by 8 plus minus 5 by 8 is equal to 0. The multiplicative inverse of 5 by 8 is 8 by 5. Because 5 by 8 into 8 by 5 is equal to 1. B. 6 by 7. Solution. The additive inverse of 6 by 7 is minus 6 by 7. Because 6 by 7 plus minus 6 by 7 is 0. The multiplicative inverse of 6 by 7 is 7 by 6. Because 6 by 7 into 7 by 6 is 1. Find the value of expression shown on screen. Solution. By solving the given expression, we get as follows. Thus, the value of given expression is minus 11 by 28.
Let us solve a few exercise problems. Click the tab to view solution.
Representation of numbers on number line. Let us recall the representation of natural numbers, whole numbers, integers on the number line. Click each circle tab to know more. Representation of natural numbers. The natural numbers are the numbers that we use to count like 1, 2, 3 and so on. The representation is shown on the screen. The set of natural numbers is usually denoted by the symbol n. Representation of whole numbers. The whole numbers are the numbers along with the 0 on the number line. The representation is shown on the screen. The set of whole numbers is usually denoted by the symbol W. Representation of integers on number line. The integers are the numbers in addition of negative numbers which are before 0 on the number line. The representation is shown on the screen. The set of integers is usually denoted by the symbol Z. Now, let us learn about representation of rational numbers on number line. Here, you can see a delicious pizza. Let us divide into 8 equal parts and represent 5/8 of pizza on a number line. Let us see how we can represent it on a number line. Consider a number line and mark 0 and 1 as shown on the screen. Let us divide it into 8 equal parts and mark them as shown on the screen. Thus, the representation of 5 by 8 is as shown on the screen. Note: any rational number can be represented on the number line. Here, the denominator tells the number of equal parts in which each unit has been divided, and the numerator tells us how many of these parts are considered. Let us observe the conversation between a teacher and a student on rational numbers between two rational numbers. Shravan, can you identify the numbers which lies in between 1 and 4? Yes, sir. The numbers are 2 and 3. Okay, can you identify the numbers which lies between -1 and -4? Yes, sir. The numbers are -2 and -3. Okay, can you identify the numbers which lie between 3 and 4? No, sir. Okay, let us know how to identify the numbers which lie between any two rational numbers. Let us consider the numbers 3 and 4 on the number line. We know that the mean of two rational numbers is also a rational number. That is, if a and b are rational numbers, then a plus b by 2 is also a rational number. So 3 plus 4 by 2 is equal to 7 by 2 is also a rational number which lies exactly in between 3 and 4. On the number line, it is represented as shown. It can be written as 3 less than 7 by 2 less than 4. Now, the mean between 3 and 7 by 2 is 3 plus 7 by 2 which is equal to 13 by 4, and it is represented on the number line as. It can be written as shown. In fact, we can find infinite number of rational numbers in between any two rational numbers. Let us see another method to find out rational numbers in between any two rational numbers. Consider the numbers 3 by 4 and 5 by 3. The denominators of both the numbers are different. By converting the denominators to become equal, we can find the rational numbers in between any two rational numbers. The LCM of denominators of 4 and 3 is 12. Therefore, we can convert the denominators of both the fractions to 12. Now, we have the rational numbers between 9 by 12 and 20 by 12 are as shown. Its number line is as shown on screen. Let us see an example on decimal representation of terminating decimal. Express the rational number 1 by 4 as decimal number. Solution. When 1 is divided by 4, we get as follows. Therefore, 1 by 4 is a terminating decimal. Let us see an example on decimal representation of non-terminating recurring decimal. Express the rational number 30 by 9 as decimal number. Solution. When 30 is divided by 9, we get as follows. Therefore, 30 by 9 is 3.3 bar, which is a non-terminating recurring decimal. Let us see an example of decimal representation of non-terminating, non-repeating decimal. Express the rational number 33 by 26 as decimal number. Solution: when 33 is divided by 26, we get as follows. Therefore, 33 by 26 is equal to 1.2692, which is a non-terminating, non-repeating decimal. Conversion of decimal form into rational form. Here, the conversion is basically of two types. They are converting terminating decimal form to rational form, converting a non-terminating recurring decimal form to rational form. Click each procedure tab to know more. Consider a decimal 13.55. Observe the given number closely and find the number of digits after decimal point. Here, we have two decimal places after a decimal point. Multiply and divide the given number with 100, since we have two decimal places after a decimal point. Then we get as shown. Reduce the obtained fraction to the simplest form, as shown on screen. Consider a decimal 0.5 bar. Let x equal to 0.5555, so on. Let it be equation 1. The periodicity is 1. So we will multiply both sides by 10. We get 10x equal to 5.555, so on. Let us represent it as equation 2. Now subtract 1 from 2. That is 10x minus x, which is equal to 5.555, so on, minus 0.555, so on. By further solving, we get x as 5 by 9. Therefore, 0.5 bar is represented as 5 by 9. Let us solve some example problems on conversion of decimal form into rational form. 0.686 bar. Solution. Let x equal to 0.686 bar, which is represented as equation 1. Here, the periodicity of the decimal is 3. So, we multiply both sides by 1000, which can be represented as equation 2. Subtracting 1 from 2, we get as follows. Thus, x is equal to 686 by 999. Therefore, the rational form of 0.686 bar is 686 by 999. 16.48. Solution. Let x is equal to 16.48. Here, we have two decimal places after a decimal point. So, we have to multiply and divide with 100. That is as shown on screen. Now, reducing the obtained fraction to the simplest form, we obtain rational number of the given form as 412 by 25. 17.58 bar. Solution. Let x be 17.58, 58, 58 and so on, and let us represent it as equation 1. Here, we have 58 is repeating after a decimal point. The periodicity of the given decimal is 2. So, we have to multiply with 100 on both sides. That 100x equal to 1758.585858 and so on. Let us represent it as equation 2. Now, subtract 1 from 2, we get as follows. Thus, x is equal to 1741 by 99. Therefore, 17.58 bar is represented as 1741 by 99.
Let us solve a few exercise problems. Click the tab to view solution. Try to solve the problems in the practice zone on your own. You can click Answer for your reference. Summary. Let us recap the highlights of this chapter.
Numbers that can be expressed in the form p by q, where p and q are integers and q not equal to 0, are known as rational numbers. The collection of rational numbers is denoted by q. Commutative property under addition and multiplication satisfies for all natural numbers, whole numbers, integers, and rational numbers. Rational numbers satisfy all the properties under addition and multiplication. Integer 0 is the identity under addition or additive identity. Integer 1 is the identity under multiplication. The multiplicative inverse of a rational number is its reciprocal. For all rational numbers a, b, and c, a into b plus c is equal to ab plus ac is known as distributive law of multiplication over addition. Any rational number can be represented on a number line. The decimal representation of rational number is either in the form of terminating decimal, non-terminating recurring decimal, and non-terminating non-recurring decimal.
Follow-up work.
Write the numbers whose multiplicative inverses are the numbers themselves. Write the rational number that does not have any reciprocal. Write 3 examples of terminating decimals, non-terminating repeating decimals, and non-terminating non-repeating decimals.
Test your understanding of the chapter by taking the mock unit test.
You have successfully completed the chapter Rational Numbers.